Hello everyone, today I am presenting my project titled Multi-Sensor Adulteration Detection System. This project explores how modern sensing technology, embedded systems, and cloud connectivity can be combined to detect adulteration in consumable substances such as liquids and food-related samples. The primary aim of this work is to create an accessible and portable detection system that allows early identification of contamination or quality degradation without the need for complex laboratory infrastructure. In this presentation, I will briefly discuss the problem addressed by the project, explain how the system works, and evaluate whether the proposed solution contributes novelty compared to existing methods. Food and liquid adulteration remains a widespread global concern affecting health, safety, and trust in supply systems. Adulteration refers to intentional or unintentional addition of unwanted or harmful substances that degrades the quality or safety of a product. Examples commonly observed include dilution or chemical alteration of milk, presence of excessive dissolved impurities in water, contamination that cannot be detected visually, and artificial treatments applied to agricultural produce. Such issues can lead to health complications, reduced nutritional value, consumer misinformation, and difficulty in maintaining quality standards. The major challenge is that conventional detection techniques typically require laboratory testing procedures involving specialized equipments, trained personnel, and significant processing time. These constraints make routine or household level verification impractical. Therefore, a core problem addressed by this project is how can we develop a compact, affordable, and easy to use system capable of providing rapid preliminary detection of adulteration indicators using measurable physical parameters. The intention is not to replace laboratory validation but to provide a first-level screening tool that empowers user and access sample quality more proactively. To approach this problem, I designed a multi-sensor integrated system that combines electronic sensing with microcontroller-based processing and cloud-based visualization. The hardware components include pH sensor used to measure acidity or alkalinity of a substance. Deviations from expected pH range may indicate contamination or chemical alteration. TDS sensors, total dissolved solids, detects dissolved ionic substances and impurities. Elevated reading can suggest dilution, contamination, or abnormal composition. Turbidity sensor measures optical clarity by analyzing suspended particles. High turbidity value indicates the presence of particulate matter or unwanted substances. Microcontroller unit, the sensor interface with an Arduino Nano or equivalent controller that collects analog data, performs initial processing, and prepares value for transmission. Circuit integration platform. Breadboard connections enable modular prototyping and allow flexible sensor expansion or modification. Cloud monitoring interface. The data is transmitted and displayed through the connected system such as laptop interface, allowing remote visualization and interpretations. The operational overflow of this work is a sample is placed into a container for measurement. Sensor capture multiple parameters simultaneously. Electrical signals are converted into digital data by the controller. Processed readings are transmitted to the visualization interface and results are displayed using intuitive color coding. Green, acceptable range; for yellow, moderate deviations, and red is potential adulteration indication. This multi-parameter evaluation approach increases readability compared to single sensor detection by providing a broader data perspective. The system is designed with emphasis on portability, low hardware cost, ease of operation, expandability for future sensor inclusion, compatibility with IoT infrastructure. It is important to acknowledge that adulteration detection itself is not a new problem. Advanced solutions already exist in the form of spectroscopic analysis, chromatography, and laboratory-grade chemical testing. However, these systems typically involve high operational cost, specialized training requirements, lack of mobility, and limited accessibility for everyday users. The novelty of this project lies not in reinventing chemical detection methods, but integrating multiple sensing mechanisms into a unified platform, providing real-time data visualization through cloud linkage, emphasizing affordability and scalability, designing for accessibility rather than institutional exclusivity. Thus, the solution contributes innovation through system integration, usability, and application context rather than fundamental sensor invention. In conclusion, this project demonstrates how embedded sensing and IoT connectivity can be applied towards addressing practical safety challenges through accessible technological design. The system provides a foundation that can be extended through machine learning based pattern recognition, development of specialized detection sensors, mobile application integration, and expansion to additional sample categories. By encouraging proactive quality awareness, this work highlights the potential of engineering solutions to support safer consumption environments. Thank you for your time and attention.